All right. So we're going to review my chapter 14, 15, and Brown is 16, and first part of 17. Covers acid bases and buffers. And we're gonna start with number 1. So let me see if I can scroll this up a little bit. Yeah, they call this a gyro mouse. There must be some little gyroscopes in here, and they can sense your movement and translate that into mouse movement. Okay, start with the easy ones first. Which of the following is a conjugate acid-base pair? Remember the conditions for acid-base pair: 1 proton at a time, and the core part of the molecule has to be the same for both of them. So that being said, the first one is I do that. Yeah. The first one doesn't have the same core molecule, right? You take a hydrogen away from HCl, you should get Cl minus, not OCl minus. So that was not it. H2SO4 looks like it's lost 2 hydrogens to get to where it's going. So that's not it. Ammonium has 1 extra hydrogen that is lost for this. So that one works. The ammonium would be the acid and the ammonia would be the base, the conjugate base. And then this one, of course, doesn't work. The hydronium to the hydroxyl, you have to lose 2 protons to get there. So that's why the answer is C. How about this? Hydrogen sulfate or bisulfate ion. Acts as in which of the following equations does it act as an acid? So an acid, according to Lewis, Bronsted-Lowry acid is an acid donate to proton. So if this donates to proton, it's got to end up with a conjugate base that looks like that. We know that. And then it's got to have a base to receive the proton, to accept the proton. So if we start out with, looks like they're all the same, and then SO4, 2 minus here. That could be that's the only one. None of the others satisfy. Let's see if the rest of it works. Water accepts the proton and becomes hydronium. That's it. So D is the answer for 2. Okay. Scroll up some more. Oops. There we go. Which of the following? It's 3. Which of the following is the equilibrium constant expression for the dissociation of the weak acid HOCl? Okay. Oops. I've done my O. What acid is that? Hypochlorous acid. So if it dissociates, and we're using the simplified version without the transfer to water, it would produce a proton plus an OCl minus. So that means its constant should be divided by HCl. And it looks like A is the best one for that one. Let's see, we're going to go down a little further and see if I can page it. Yeah, got lucky. 6. A solution that has a pOH of 12.1 would be what? Very acidic, slightly acidic, neutral, very basic, slightly basic. Okay, remember the pKw equals pH plus pOH. pKw is 14. That's for water. And if this one is 12.1, then pH would be 1.9. That looks pretty acidic to me. That's why the answer is A, very acidic. How about 7? Which of the following indicates the most basic solution? Okay, let's look at our choices. It's also got at least 2 of the solutions are equally basic. So in that case, we're sort of obliged to investigate each one and compare them. So for A, if we're looking, I would go for calculating the pH. So what's the pH of the first one? The negative log of this number would be 10 with it. How about B? pOH is 6.7, so it's 14 minus 6.7, which is equal to 7.3 pH. Okay. How about C? pOH is 7 times 10 to the minus 5th. So that's going to take a little more doing. Where's my calculator? Here it is. So that would be pOH would be 7 exponent minus 5, and then take the log of that, change the sign. So that's 4.15. pH then would be 14 minus that one. Oh, 10 point. No, it would be 9 something.
9.85.
Yeah. Okay. And how about D? That one gives it to us. 4.2 pH. Okay, so we got this one, that one, and that one. Most basic. It's like this one. Yep. Let's see, we can still see 8. All of 8. Which of the following solutions contains the strongest acid? Okay, this is not, you don't have to calculate the pH of this solution to know which is the strongest, because in chemical terms, strong and weak refer to the equilibrium expression. How far does the equilibrium expression go to the right to tell you whether it's the strongest acid? And that means we need the largest K value, right? We need a big numerator and a small denominator. And to do that, the Ka needs to be large. So the largest Ka of this bunch is this one, 7.2 times 10 to the minus 4th. If you look at the powers of 10, right, you find that there's minus 10, minus 5, minus 5, minus 8, minus 4. You don't even have to look at the coefficients. If you get 2, say our selections only gave us these, then you would go to the coefficient and say, all right, that was bigger than this one, so this one would be it. But that's the strongest acid is E. And I stuck this one in here just for argument's sake, which has the strongest conjugate base. The strongest conjugate base is made from the weakest acid. So the weakest acid would be the one here. Yes, with the smallest K would produce the strongest conjugate base. So we change the wording to include this rather than that, then B would be the answer. Oops, wrong direction, sorry. 9, there we go. Which of the following statements are true? Let's see, all the statements are false, at least 2 are true. Okay, so we're looking at A, B, and C, actually. The pH of a strong acid is always lower than the pH of a weak acid. What's wrong with this picture? The pH is a extensive property. When we say strength, weak or strong acid, we're an intensive property. It's characteristic of the molecule. So the pH of a weak acid could be lower than the pH of a strong acid. It depends on the concentration. So A is false. How about the pH of a solution can never be negative? Is that true? Think of what pH is. pH is negative log of the hydrogen ion concentration. Right? If you get this number big enough, you can make it negative. If it's really small, then the log of it will usually come out as a negative number, and then a negative gives you a positive. But if this is the very large hydrogen ion concentration, it could come out a log of that would be positive, and then your value would be negative. So that one's false also.
What would that what would a negative pH look like in a solution?
I mean, how could we produce a negative?
Yeah.
Let's say we had let's say we had 10 molar HCl. Okay, so the negative log of 10 be, what's the power of the base number 10? What's the power of 10 that makes it 10? 1, right? Okay. So you got a negative 1 pH. Oh, we didn't do C. For a conjugate acid-base pair, Ka equals 1 over Kb. Is that true? No. Remember, Kw equals Ka times Kb. So Ka would be Kw divided by Kb. So that 1 should actually be Kw. All right. Oh, so the answer is E. All of them are false. Let's see. How do we pick up 11? Let's see if I can scroll it. Not as easy as it looks. Okay. There we go. Okay, for 11. Oh, by the way, this is chapter 14. I forgot to write that up here. This one is chapter 14, 11. We've been in chapter 14 for the benefit of our viewing audience. For the stepwise dissociation of aqueous H3PO4, which of the following is not a conjugate acid-base pair? So the stepwise dissociation of H3PO4 produces what? 1 hydrogen and an H2PO4 minus. Still picking that up? Yeah. Then we would take H2PO4 minus and give us another proton, HPO4 2 minus, and then HPO4 2 minus gives another proton plus PO4 3 minus. So that's the stepwise dissociation. This conjugate base becomes the acid for the next reaction. And this conjugate base becomes the acid for the final one. Okay, let's see, what do we have? Which of this not conjugate acid base pair? HPO4 2 minus, PO4 2 minus, and PO4 3 minus. Okay, A is good. How about B? H3PO4 and H2PO4 minus. That one's good. C, H2PO4 and HPO4 2 minus. That one's good. And D, H2PO4 and PO4 3 minus. Nope. D's wrong. How about E? Why do we throw E in there? Because these two are always in the solution. No matter what else is in there, they're always there. So H3O plus and H2O are present as conjugate acid base pairs in that solution. Okay, so D's the answer for number 11. 12. For which of the following 0.1 molar diprotic acid, 0.1 molar diprotic acid. So it has two protons like that. Would the second dissociation affect the pH significantly? Remember, when it dissociates, the second pH, the second K is always less than the first K. Sometimes it's way, way, way smaller. Sometimes it's pretty close. So the effect that the second one would have on the first one depends on whether the second Ka is close to the first one. So let's see. This one is -2. The second one is -7. That's way far away. It's 5 orders of magnitude. That won't have an impact. This one is 4 orders of magnitude. This one's 5 orders of magnitude. This one's only 1. And besides that, this is 9.3. It's almost that one. It's really close. So D, for that H2D, the second dissociation would have an impact on the pH. All right. Page it until we get in the vicinity. There we go, 16. Which of the following, let's see, let's spend more time off camera. Which of the following would give the highest pH when dissolved in water to form a 0.1 molar solution? 0.1 molar solution. And we're looking for the highest pH. Okay. Well, let's see, we can eliminate some of them. A strong acid would more than likely be the lowest pH. A weak acid would be an acidic pH, but it would be a lower pH, a higher pH than this one. How about, it's one of these, the potassium salt of a weak acid. So what would that do? Potassium salt of, say, a weak acid dissociates into K and A minus. So you have to look at it this way. If that's a weak acid, then it's going to produce this plus that. Okay? If that's a weak acid, this is a strong base. So what it does is this interacts with water and produces HA plus OH minus. And it's way, way over on this side. Okay. So the potassium salt of a weak acid would produce a very basic solution. The potassium salt of a strong acid would produce a neutral solution because KOH is a strong base and the strong acid, strong base makes neutral. The ammonium salt of a strong acid. The ammonium salt of a strong acid, like what? This, something like that, HCl and ammonium salt. So this would dissociate like this. And this would do that. This is not going to react with anything. Chloride won't react with water. So this is not going to produce anything. This would interact with water and transfer over there to H3O plus NH3. That's an acidic solution. All right, so we found our answer C. That's the most basic one. Let's see. 19. Oh, I see. The key is this is not capitalized, so it's probably got something above it that's talking. Here, 17 through 20. Select the answer that best describes an aqueous solution made from each of the following substances. So we'll go back down here. Aqueous solution of solid ammonium acetate. So for ammonium, the Ka is 10 to the minus 10. And for acetate, Kb is 5.6 times 10 to the minus 10. These are competing. This is competing for delivering a proton to water, and this is competing for extracting a proton from water. And they're equal in strength. For this base versus this acid, this would be a neutral solution. This is one of those cases where when you combine weak acid, weak base together, you have to know what their relationship is in terms of the reactions they're going to undergo. And if the Ka and the Kb are equal, you get a neutral solution. A rule of thumb won't work for this one. 20. Again, we're going to make a solution with ammonium perchlorate. Right. For this one, you can use a rule of thumb because ammonium is a weak acid, or it's derived from a weak base, ammonia, versus a strong acid. So a weak base, strong acid gives you an acidic solution. Now that's the rule of thumb. That gives you the acidic solution. And you can compare the values actually. 10 to the minus 10 versus 21, so the acid wins. Okay, we're out of that group now. 22. Which factor listed below is most important in determining the strength of an oxyacid? Oxyacid. Okay, something like HClO, ClO2, ClO3, ClO4. The strength of an oxyacid. What determines the strength of an oxyacid? The number of oxygens. That's pretty straightforward. Number of oxygen atoms in the molecule. The reason it is because you get, let's see, I painted myself into a corner. I'm looking for the right word. The oxygens on this chlorine tend to draw electron density away from the chlorine. And then it draws electron density away from the hydrogen, which weakens the bond between the hydrogen and the chlorine. And the more oxygens you have, the weaker this bond, which makes a stronger acid. The proper chemical term for it escapes me for the moment. 24. Which of the species below, when dissolved in water, will not produce a basic solution? Okay, well, what reaction? This looks like we've got a combination of situations here. We've got the ammonia, right, which will react with water to produce ammonium plus OH minus. So that'll make a basic solution. Then we look at, well, barium hydroxide obviously makes a basic solution. If you put it in water, the hydroxides dissociate, and there you are. But the key here is the difference between this one and this one. This is a metal oxide, this is a non-metal oxide. Remember, non-metal oxides make acids. Metal oxides make bases. So the SO2 will react with water and produce H2SO3, which is an acid. The barium oxide will react with water to produce that. Yeah. So metal oxides make basic solutions and non-metal oxides make acidic solutions. Which of the following species cannot act as a Lewis base? Okay. Lewis base. Go back to our definition. A Lewis base, Lewis acids and bases refer to acceptance or donation of electron pairs. So a Lewis base would donate an electron pair, whereas a Bronsted-Lowry acid donates a hydrogen. A Lewis acid accepts an electron pair. Look at it this way. So electrons, there's a bond here. Right? 2 electrons. So these 2 electrons go here. That leaves this with a positive charge. So this is a Lewis acid because it donates a proton or it accepts an electron pair. So acting as a Lewis base requires that it has to accept an electron pair. Excuse me. Donate an electron pair, excuse me. Donate an electron pair. So which one can or cannot donate an electron pair? Well, that one's got some extra electrons, doesn't it? That one's got an extra electron that it can donate. How about CH4? It has no electrons to donate, right? Methane can't donate. That's why the answer is C. If we look at H2S, right, we'd have to draw the Lewis structure for that. Why don't we do that? Sulfur is 6, and this is 2, that's 8. So we'll have sulfur, hydrogen, 2, 4. We need 4 more. 1, 2, 3, 4. Right? So it's got some extra electrons to donate. So it's a base. And NH3, we know NH3 is There's your pair to donate. So it would make a base too, a Lewis base. Right, so the only one that doesn't have any electrons to donate is ethane. About 26. Which of the following species cannot act as a Lewis base? Oh, there's another one. All right. Well, it looks to me like this one's got electrons to donate. That one's got a few. Any of these negative ions can donate. And this one's got a lone pair. Right? We just showed that one. But this one, ammonium, has no donatable electrons because it's got 4 bonded hydrogens on there and no lone pairs. In fact, it would be better as a Lewis acid because of that charge. So that's why easy answer for this one. Now I'll see if I can do this. That's far enough. Okay, 27. Which of the following species cannot act as a Lewis acid? Okay, let's see. Lewis acid would be electron pair acceptor. So which one can accept electron pairs? Well, those positive ions, I bet they could accept electron pairs. That one accept one, that one accept one. H minus, I mean, it's hard enough to get an extra electron on hydrogen because it's got an s orbital that's got room for 2 electrons, but you try to push more electrons onto it, it just won't work. So easy answer to that one. It's not a Lewis acid by any stretch of the imagination. How about this one? Let's see what we got going here. Given the following values of pKa for each of these acids, determine which is the weakest base of the answers listed. Okay, so a strong acid makes a weak base. That's what we're looking at. So if we dissociate this one, we should be ClO2. But that's a strong acid, right? It should make a weak base. And it looks like it's the strongest acid of the bunch. So it would make the weakest base. So ClO2 minus would make, give the following, determine which of the weakest base. Oh, trick question. We left out that one, which has a pK of doesn't matter. It completely dissociates. There's no equilibrium involved. So it produces a chloride ion that has no interest whatsoever in taking a hydrogen from water. So that's why this is the answer. I almost got stumped by my own question. Let's see. I need a drink. I'm skipping a bunch of. Here we go. Carbonic acid, 38. Carbonic acid. What is carbonic acid, by the way? Right. That's carbonate. 8's become X, carbonic acid. Is a diprotic acid with a Ka1 of 10 to the minus 7th and a Ka2 of 10 to the minus 11th. Okay. The ion product for water is 10 to the minus 14th. Okay. What's the OH minus concentration of a solution that is 0.18 molar in sodium carbonate. Okay, here what you do is say sodium carbonate. What's it going to do in aqueous solution? It's completely soluble, right? All sodium salts are completely soluble. So what it's going to make is sodium ions plus carbonate ions. In fact, it'll make two of these. Well, now you ask yourself, in this solution, at the very beginning, before any reactions occur, I mean, after this dissociates, what are the major players? What are the ions? Well, we got sodium, of course. We got carbonate. And we got water. That's it. Those are the major players. Sodium's not going to react with anything. It's not going to get back together with carbonate because it's totally soluble. It's not going to react with water. Just because. It has no interest in water. Okay, so what we've got is carbonate and water reacting. So let's look at the information we're given. Let's see. The ion product for water is this. Okay. When this carbonic acid is in solution, it could go to this one, right? That's the Ka1. Or it could go like this, CO3 minus 2H plus CO3 2 minus. This is the Ka2. Okay. So we're actually starting with this one, which means based upon the Ks, this is the stronger base. Right? What it's going to do is it's going to latch on to a proton from water and go back this way. Right? Because it's such a small value, right here, it's such a small value, it's going to go back this way. And when it latches onto that proton from water, it's going to leave behind a hydroxyl. Okay. So what does that mean? That means that we need make some more room. The controlling reaction is going to be 2 minus plus water yields HCO3 minus plus OH minus. Okay. Now, we don't have a K for this one. This is a KB. You can tell because water is a reactant and the proton is transferred over. Okay, so what's the KB for this reaction? Well, we need to go to the Ka2 and find out what the KB is. So the KB is going to be Kw divided by Ka, which is 10 to the minus 14, divided by 4.8 times 10 to the minus 11. So that's the equilibrium constant for this reaction. Let's see. And 4.8 divided into that. 2.08 times 10 to the minus 4. 2.08 times 10 to the minus 4. Okay. Now, once we get to this point, who's to say we don't want to go back that way? Well, we got to do one at a time anyway. So let's set up a let's see, 0.18 molar. 0.18 molar in sodium carbonate. Oh. I missed a point. we're starting with this because it's sodium carbonate that goes into solution. No, I didn't miss that. I did say that before. I erased it. That's why I missed it. Okay, so we're starting with this, and it's 0.18 molar in this right here to begin with, 0.18 molar in carbonate. So how much of these two does it produce? Well, it's going to, this is initial, this is change. So it's going to lose some, and it's going to produce some of that, some of this. Okay, so we're going to have, at equilibrium, we're going to have 0.18 minus X, and then X, and then X. And if we write the equilibrium expression for this, it's going to be equal to that value, the KB. Right? So we'll have this term, and this term. We're going to have KB 2.08 times 10 to the minus 14 equals carbonate, HCO3 minus OH minus divided by CO3, 2 minus. There we go. Now that we got that, I have to keep erasing stuff. Then this is going to be equal to 14. Oh, excuse me, 4. There we go. This is going to be X, this is going to be X, so that's X squared in the numerator. And then 0.18 minus X in the denominator. Right? We don't want a quadratic. Right? So is this X going to be small enough? If well, yes, because this is 10 to the minus 4, it's going to be like 10,000th of the change. So we can say that's gone, and we can say now this one times that one, 0.18. Is over here on this side, 3.75 times 10 to the minus 5 equals X squared. And that X then is the square root of that value, which is 6.12 times 10 to the minus 3. Now, X was one of these values, which is the OH concentration, right? Okay, so POH is the negative log of this value. POH equals the negative log of that value, which is 2.21. And pH is 14 minus that. 11.8. Oh, that's not what it asked for, is it? What's the OH? Wait a minute. Oh, I already got the answer. I was going too far. Now, yeah, if we want to be sure that this is the controlling reaction, then we look at KB for the other one, right? Once it gets to this point, does it keep going to H2CO3? And you compare the KBs. So the KB for this one here would be 10 to the minus 14 and divide by that value. So that's 2.38 times 10 to the minus 8. 2.38 times 10 to the minus 8, right? This is the controlling reaction. Because the first reaction here, it won't go all the way back here. It's going to stay with this one because it's 4 orders of magnitude bigger than that one. Okay, in case you're interested. I mean, that's one thing that occurred to me. You know, it's diprotic. I mean, why didn't it go all the way back? Well, that's the reason. That one took a while. Okay. How are we doing on time? 2 o'clock. $39. Calculate the pH at equivalence for the following titration: 0.1 molar HOCl, 0.1 molar sodium hydroxide. At equivalence. Okay, let's see. What do we have here? I'm going to move over here and write some of this stuff here. So at equivalence, what do we have? We have hydrogen ion equal to hydroxyls. That's what equivalence means. Okay. So if we have 0.1 molar HOCl, 0.1 molar HOCl, and 0.1 molar sodium hydroxide, they're the same concentration. See, I left out my zeros there. Since they're the same concentration, then they would be they would need equal volumes of each one to have this acid neutralized by this base. Okay. So that's nice of the person who ever wrote this question. So for this problem, you have 2 steps. One is the stoichiometry. You're going to neutralize these acids, and then you're going to go to an equilibrium problem. Stoichiometry first, then equilibrium. So if we have, since we don't have a volume, we know the volume is going to be equal. So we can just make up a volume. Say this one's going to be 100 mils. That means this one has to be 100 mils. Okay. So this is going to be 100 times 0.1. And I'm going to use millimolar. Did I explain millimolar before? Milliliters times molarity is millimoles. So 100 times 0.1 is 10 millimoles. And this one's 10 millimoles. And by the way, once we go back the other direction, once we need to calculate concentration, millimoles divided by milliliters is molar. Okay, so we're going to have a reaction where, let's see, before and after. So before we have 10 millimoles of hydrogen ions. Wait a minute, that's not what I want to do. We start off with HOCl and sodium hydroxide. So before we start, we have 10 millimoles here, and we have 10 millimoles here. When they react, we end up with, let's see, we have 10 millimoles of water. We also have 10 millimoles of OCl minus, and we have 10 millimoles of sodium. There we go. So which one? Now we're going to have an equilibrium. We know we've got this much of that one and this much of this one because the hydrogen and the hydroxyl are now water. So sodium's not going to react with anything. So the dominant species in water, now we're starting with OCl minus. So we've got OCl minus, which is 10 millimolar. And we've got water. And it's going to react and produce what? HOCl plus OH minus. Okay. So this is where we start. Initial, change, equilibrium. And we essentially have 0 of these to begin with. We have a little bit of that, but not much. Okay. Now this stoichiometry we can do with actual amounts, but equilibrium we have to have concentrations. So this has to be divided by the total volume. Right? 10 divided by 200 is 5 divided by 100. Let's see. 1 divided by 20. 0.1 divided by 2. No, that's not the way to go. 5 divided by 100. So that's move 2 places. 1, 2, 1, 2. So it's 0.05 molar. There we go. That's our starting position for OCl minus. Okay, so the change, we're going to go this direction. We're going to lose some. It's going to end up over here. Right? We're going to have 0.05 molar minus X. We're going to have X and X. But the equilibrium expression is not an acid expression, it's a base. So what we need is the Kb. Right? So the Kb for this one is 10 to the minus 14 divided by 3.5 times 10 to the minus 8. .86 times 10 to the minus 7. That's the Kb for that reaction. Now we can say, we know this one times this one divided by that one, which would be x squared over 0.05 minus x equals 2.86 times 10 to the minus 7. And since that value is so small, we're not going to get a whole lot of it going this direction. So this is going to drop out. So 0.05 times that number is 1.43 times 10 to the minus 8. And then x is equal to the square root of that value. 1.19 times 10 to the minus 4 molar hydroxide. And it asks us for what? What's the pH? So the pOH would be negative log of that, which would be 3.92. pOH equals 3.92, and pH is 14 minus that. 1.08. Oops, no. My decimal point. 10.1. There we go. That was a lot of work. But this problem was to emphasize the point that these titrations, in order to find out what the pH at a certain point on the titration curve, and you can do that for any point of the titration, if you're given enough information, to run it as a stoichiometry. And then you go this way and then you come back as an equilibrium. Oh, that's it for 14. You need a restroom break? Are you good? Okay. Well, let's go to chapter 15. Go. Let's close this document. How's it setting? That's not bad. Let's scroll down to the first available. There we go. All right. So now we're into chapter 15 in my book, which we're on the way to buffers. All right, number 4. A weak acid, HF. Is that true? HF is a weak acid. It's a halogen. Yeah. The rest of the halogens are strong. HF is unusual. It's a weak acid. It's in solution with dissolved sodium fluoride. Okay. You got your acid and your conjugate base. If HCl is added, which ion will react with the extra hydrogen ions from the HCl to keep the pH from changing? Okay, so we're actually looking at an equilibrium where HF produces its conjugate base. And if you add hydrogen ions to this expression, where do they fit in? They fit in right here. So we add extra hydrogen ions, they react with the F- fluoride ion. That's why the answer is C. 5. Which of the following is true for a buffered solution? Well, let's see. We have a selection down here that says all of these. Okay, so that means we got to look at every one of them. Which of the following is true for a buffered solution? The solution, let's put A. The solution resists change in its hydrogen ion concentration. Yep, that's true. The solution will not change its pH very much, even if a concentrated acid is added. That's true as far as it goes. It actually depends on how much of a concentrated acid you add. But as far as that statement goes, it's true. The solution will not change its pH very much, even if a strong base is added. That is also true. D. Any hydrogen ions will react with a conjugate base of a weak acid already in solution. We just showed that with fluoride ion. The fluoride ion was the conjugate base of a weak acid. That's what reacts with the hydrogen ions. So all of them are true. All right. Let's see. Let's see if I can scroll this up. That's good. 8. How do the pHs of buffered solutions compare? The pH of buffered solution 1, oh, I'm sorry. I scrolled too far. Other direction. There we go. So you have these two buffered solutions. Solution one consists of 5 molar HOAC and 5 molar sodium acetate. Okay. Is that a buffer? Yep. You got equal concentrations of acid and conjugate base. That's a perfect buffer. Okay. How about solution 2? Okay, solution 2 is 0.05 molar acetic acid. That's what that abbreviation is. That's abbreviation for OAC is acetate, and you add a hydrogen, you get acetic acid. And this is sodium acetate. I didn't make that clear at the beginning. And then you got the 050 molar sodium acetate. Okay, they're both buffers. Okay. Got equal amounts of acid and conjugate base. All right, remember Henderson-Hasselbalch equation. pKa plus log of conjugate base over the weak acid. So if these are equal, that means this is log of 1, which is 0. And that's a perfect base. I mean, perfect buffer. The question is, how do the pHs of the buffered solutions compare? They're exactly equal, right? It's right smack dab in the middle of the buffer zone. So if we look for the one that says one's not greater than the other, pH of buffer 1 is equal to that of buffer 2. That's it right there. C. 9. Which of the following is the net ionic equation for the reaction that occurs during the titration of, oh, okay, we got different conditions now. I'm gonna leave that there. 9. Which of the following is the net ionic equation for the reaction that occurs during titration of nitric acid and potassium hydroxide? That's kind of a trick question. What's the net ionic equation for all acid-base reactions? That's it. Let's see, I need to scroll down a little bit. Go. Okay, 10. In the titration of a weak acid HA with sodium hydroxide, the stoichiometric point is known to occur at a pH value of approximately 10. Okay, so that's the equivalence point. It's pH 10. Which of the following indicator acids would be best to use to mark the endpoint of this titration? What you try to do is, if the endpoint, that's not correct, endpoint, equivalence point is equal to pH 10, you want your indicator, pKa, to be approximately equal to that pH. Okay, or as close as possible. So which one's closest to 10? Now this one's 4 orders of magnitude away, that one's 1 order away, that one's 2 orders away, and that one's 4 orders away. I'd say this one would work best. The Ka for that indicator. Would work best. Let's see here. Scroll just a tiny bit. All right, 13. Which of the following solutions would be described as a buffer solution? Okay. What are the conditions for a buffer? First of all, you need a weak acid most of the time. Weak acid and its conjugate base. So the base has to lose one proton. So let's see if we've got any candidates here. Acetic acid and hydrochloric acid. Nope, sorry. They're both acids. This is a strong one. Acetic acid and sodium hydroxide. Possibly. Why? Because the sodium hydroxide would partially neutralize this and leave you with your conjugate base. Right? So this is maybe. That one's definitely no. That one could be. How about this one? Sodium bromide. Well, that's not a weak acid. Can't be. Ammonia and sodium hydroxide. Well, you're adding the base with the base. So that can't be either. Hydrochloric and sodium, that's going to be neutral. All right. So by process of elimination, this one should be it. And what you end up with is 0.2 molar. Okay, it doesn't tell us the proportions of each. So you could add enough of this to neutralize half of that. And if you did that, you'd be right in the middle of your buffer zone. That's one way to make a buffer. The simplest way is to take maybe sodium acetate of an equimolar amount and put them together in equal volumes. And that'd be a perfect buffer. But you can make a buffer this way. Let's see, that was, now we need 14. Which of the following mixtures would be classified as a buffer solution? Okay, similar reasoning as before. No weak acid in here. Okay, there's weak acid in each one of these. This is one way to write acetic acid. Have I shown you that before? You normally see acetic acid written this way, C2H3O2. There's your acid proton. But if you write it with a little bit more structure, you find that you've got a methyl group right here attached to another carbon. And then on this carbon, you've got like that carboxylic acid group. So that's 3, 4, 1, 2, 3, 4, 2 carbons, 2 oxygens. Okay. This way, you see that the acidic hydrogen is part of the carboxylic acid group. And we write it like CH214 C14. That's why it's written that way. Okay, so let's get back to, we counted this one out, right? HCl, that's not a weak acid. Okay, we've got weak acids here. And we can count this one out because when you add acid to this one, it's just going to make it more acid. It's not going to make a buffer out of it. Right, so B, C, and D are possibilities. What you want is to add enough of this one. Looks like it's the same thing. We're adding this to acetic acid. So you want to add enough of this one to neutralize about half of it. So 55 milliliters of this plus that would go past the equivalence point. You don't have a buffer anymore. This one, 25 milliliters of an equal concentration would exactly neutralize half of this and leave you with a conjugate base of equal concentration to the acid that's left over. This one would be perfect. This one, you don't add nearly enough. a half a mil of that concentration, it won't get you anywhere near the buffer zone. So C is the best answer. All right, let's see. Consider the following indicators of their pH ranges. Okay, so this tells you the pH, the ideal pH range for using each one of these indicators. Assume an indicator works best when the equivalence point of the titration comes in the middle of the indicator range. Okay, for which of the following titrations would methyl red be the best indicator? Methyl red is here. Right. So what's the middle of that range? For 10.8, it'd be 4.9. 0.8. Yeah. No, 5.4. 5.4 would be the middle of that range. Okay. So, for which of the following titrations would methyl red be? Well, this is a strong acid and a strong base. It's going to reach equivalence at pH 7. It's nowhere near that one. Strong acid, strong base. Aniline, 10 to the minus 10, and this one. So it's pKb would be in the neighborhood of 9 or 10. So it's way off. I mean, you can run it, you can do the calculations. How about this one? 1.8 times 10 to the minus 5. So what would the POH be for that one? I mean, the pKw, the pKb for this one is 1.8 to minus 5. That's 4.74. Pretty close. How about this one? 7.2. Oops. 7.2, 10 to the minus 4. Log, changes that. This will be 3.14. Getting further away from it. And acetic acid, 1.8 times 10 to the minus 5. Well, that would be 4.74 also. But this is pKb, this is pKa. So how do we distinguish the difference between the two? Which one would be best? Are there any indicators up here? Equivalence point for which of the following titrations would methyl red be the best indicator? I might have to consult my discussion on that one. 19. Are you looking at it? Yes. C. What does it say about E? Oh. E. Acetic acid plus sodium hydroxide. Okay, now why did I do that? To find the KB. Oh. All right. Okay, so when we do this titration, I didn't do the stoichiometry first. The stoichiometry neutralizes this acetic acid and produces acetate in a certain concentration. And then the acetate is the return reaction for equilibrium. So that's how you decide that C is the best answer. Actually, the pH for this one is going to occur at 8.72. That's the pH at neutralization. Yeah. Okay, so that's why C is the best answer for this one. You have to actually calculate the pH at equivalence in order to answer that question. Oops. Uh, 23. 50 milliliter solution of 0.035 molar hydrocyanic acid is titrated with a 0.0333 molar solution of sodium hydroxide. What's the pH of the acid solution after 15 milliliters of titrant have been added? Okay, in this one, we do have to do a stoichiometry followed by an equilibrium. Yeah, stoichiometry followed by equilibrium. Okay. So the stoichiometry is going to be, refresh my memory. Yeah. So we've got hydrocyanic acid, and then we've got sodium hydroxide, and it's going to produce water plus sodium cyanide. Okay, so we're starting off with 50 milliliters of 0.035 molar here, and 0.0333 molar of sodium hydroxide. $15 milliliters of titrant have been added. This is the titrant. 15 milliliters. Okay, now we have our stoichiometry. So before, we have how many millimoles of HCN do we have? 50 times 0.035. We have 1.75 millimole of that one, and 15 and 0.0333. So this one is 0.4995 millimoles. Okay. When they react, notice they're 1-to-1, OH, H. So this one's going to be used up completely. And it's going to produce, this is before and after, it's going to produce 0.4995 millimoles of sodium cyanide and 0 sodium hydroxide, but it's going to have some of this left over. So since they're 1-to-1, what's left over is this one minus that one, which is 1.251. 251 millimoles. Okay, that's our starting point for the reaction of, let me see. Yeah, HCN and H plus Cn minus. So initially, we're starting off now with 1.251 millimoles divided by what's the volume? 65 milliliters, right? And cyanide ion is 0.4995 divided by 65 is equal to, okay, 1.92 times 10 to the minus 2 molar. This one is 0.4995. This one is 7.68 times 10 to the minus 3 molar. That's initial. Change, equilibrium. Okay, which way are we going to go? Well, we've converted all the hydrogen ions over here that we are going to make into, so we don't have any hydrogen ions to speak of over here. So that means the reaction is going to the right. So we're still going to lose some HCN, and it's going to produce an X here and an X there. So this is 1.92 times 10 to the minus 2 minus X. This is X, this is X. Now we can run our equilibrium expression. So Ka for acetic acid, for hydrocyanic acid is 6.2 times 10 to the minus 10. So that means not very much of this is going to be produced. That means we can ignore this X. That means it's X squared divided by 1.92 times 10 to the minus 2. And then we multiply this one times that one. Let's see. 6.2, 10 to the minus 10. Okay. Times, and then take the square root of it. So I get X equals 3.45 times 10 to the minus 6 molar. And this is equal to hydrogen ion concentration. Okay, and it asks us pH. What's the pH of that solution? Okay, so I need to take the negative log of that value. 5.46. 5.46. Yeah, wait a minute. What did I do wrong? Oh. Boy, that was dumb. That plus that. So it's not X squared. It's X times 7.68 times 10 to the minus 3 plus X. So can we simplify that? I think the idea is to leave this X here. Multiply this one times that one. I'm going to save myself some time. Multiply this one times that one. So it's this one times this minus this one times this. Yeah. So that's 1.2 6.19 times 10 to the minus 11 minus 6.2 times 10 to the minus 10 x equals. And then this one is left over as 7.68 times 10 to the minus 3 x plus x squared. This one times that one, and this one times that one. I did a quadratic on this. So you end up with x squared plus 7.68 times 10 to the minus 3 two x's there. I wonder if that's right. Because I need to bring this x over here to this one, makes them both negative. I think that I may have calculated that one wrong. Right? This one times that one. This one times that one is on this side. This one comes over here. That one times that one. That one looks right. And then this one times that one. So we're good up to here. I'm gonna move over here. In this case, I want to put 0 on one side and everything else on the other side for the quadratic. So that means this x squared stays over here. This positive 7.68 10 to the minus 3. Oh, I see. Look, when you add this much to that number, 10 to the minus 3, 10 to the minus 10, that number is insignificant. That's why we had 7.63 times 10 to the minus 3, and then minus 1.19 times 10 to the minus 11 equals 0. Then we solve the quadratic. Oh, this needs to be an x. There we go. So once you solve the quadratic, you get hydrogen ion concentration of 1.55 times 10 to the minus 9. Take the negative log of that, you get pH 8.81. Here. That was a bear. All right. Let's see how much more trouble I can get myself into. 25. A certain indicator, generic HIM, has a pKa 9.00. And a color change becomes visible when 7% of it is IN minus. So it's going to dissociate to this and this, okay? And the color change becomes visible when 0.07 of it is in this form. and what pH is the color change visible. Okay. We can use Henderson-Hasselbalch for this one. So this is going to have IN minus here and HIN there. This pKa is 9. And this is going to be 7%. So this is going to be let's see, am I doing that right? I'm second guessing myself there. Yeah. 7% is as IN minus. So this is actually log of 0.07. .07 and add that to 9. So 7.85 pH. Okay. I think I was trying to make it more complicated than it was. Let's see. 26. In the figure below, okay, let's see if I can do this. Oh, okay. In the figure below, the pH at first hydrogen ion equivalence is approximately what? Okay. At first hydrogen ion equivalence. There's the first hydrogen, there's the second hydrogen. The first one, pH at 6. That's the equivalence for the first hydrogen. Here. Okay. In the figure below, the acid would best be used in a buffer near pH. So 1, 4, 6, 10, 12. 1, 4, 6, 10, 12. If we want to make a buffer out of it, then we need, and we need to find this region in here. This one would be best buffered at around 2.5. And this end would be about 9.6 or 7. So this might work, but there's no 2's in there, right? So 10 would have to be the best one. Yeah, D. That makes sense? Okay. Oh, that's it.